Thank you, Greg. Thanks to Ilya and all the organizers for having me here. So my name is Andrew, and I'm coming to you from Purdue, where I've been a professor in the physics department for the last 5 years. These lectures all have these nice short titles, so I'm going to talk to you about sensing. And I think on some versions it's even been lengthened to cell sensing. And so I've called my lectures the physics of cell sensing, just to remind everyone that this is a physics school, a condensed matter school, in fact. So that's my plan, physics of cell sensing. I guess I've also been encouraged to use the board. Other people, I'm sure, have followed suit. I'm not going to use a computer, if that's okay. So the main theme of what I'm going to tell you about this week is to try and understand, using tools from physics, how cells are so good at sensing their environment. So this is driven by experiments, ultimately, because experiments show some amazing things about what cells can do in terms of sensing. Cells sense many things, but one of the most common is they sense the concentration or the change in concentration or a gradient in concentration of molecules in their environment. And experiments make clear that they're very good at that. It's also kind of reasonable that they're very good at that, because that's, a very important component of fitness. And as an example, there are some cells that can detect a single molecule, a single event of a molecule binding to their surface, for example. So olfactory cells, the smell sensing cells, have been shown to detect single odorant molecules, for example. T cells, immune cells that react when you have a foreign pathogen in your body, they've also been shown to initiate an internal response when they detect one special molecule called a peptide, that's sort of the representation of some foreign agent. And amoeba, right? Single-celled organisms that are very good at tracking changes in chemical concentrations have been shown to essentially be able to detect a difference in the number of molecules binding their right side and their left side of only about 10 molecules. Right? So these are very fascinating observations, and we want to try to understand them using physics. And at first you might think, oh, well, that's sort of stupid, because you need to know how these molecules are binding. You need to know a lot of sort of the mechanics of the receptors and the biology of how that signal gets transmitted inside the cell. And I guess it probably won't be unfamiliar to you that we can take a different approach. We can just sort of start simple and ask what kinds of limits the actual problem of sensing any sort of set of diffusing molecules places on any sensor, be it a cell or otherwise, and obtain some nice quantitative results and then see how those results actually compare to the experiments. Okay, so I'm going to take a bit of a historical approach. I'm going to start with some seminal work by two physicists, well, one biologist / physicist and one physicist, named Howard Berg and Edward Purcell. They started thinking about cell sensing in 1977, and I'm going to sort of transition to more modern works, including, if time, some of the things that I've been working on. But it's good to put that in just in case there's not time. So the plan is to talk first about single cells and how they sense concentrations in their environment, following the works of Berg and Purcell. Then talk about single cell sensing concentration gradients, following more recent work. And then talk about how cells can work together to do this job. Most cells don't, live alone. Almost all cells communicate, and sometimes communication can play a role in the sensory process as well. Good. So if that sounds good to everybody, I'm going to start with the work of Berg and Purcell starting in 1977. And just so you guys have a little bit of background, are people familiar with Howard Berg, the work of Howard Berg? Okay, a few people. So Howard Berg is probably the leading expert on E. coli bacteria and how they sense their environment and how they then move in response. He's an experimentalist. As far as I know, he's still very active. He's at Harvard. An interesting tidbit is that the work he did with Edward Purcell was done while he was a professor here at Boulder, actually. But he then subsequently moved to Harvard. Edward Purcell is more of a traditional physicist, at least he was for most of his life. He won the Nobel Prize for discovering and understanding nuclear magnetic resonance. But toward the end of his life, he started getting really into cell sensing and cell motion and how cells live under very different physical constraints than larger things like other animals like us. And so they got together in 1977, or I guess shortly before, and started thinking about what are the physical constraints on a cell sensing its environment. So, I want to start thinking about the problem by drawing a cell, okay? This is kind of wiggly in shape. We're going to soon make it a sphere, not to worry. But I want to start by sort of just giving the basic premise of how cells perform a very important task, which is to estimate the concentration of a particular molecule of interest in their environment, right? So the idea is that, let's say this is, an important nutrient or maybe something bad that they want to run away from. The molecules that make up this concentration are, of course, diffusing around in a random manner. We can give them a diffusion coefficient D. But otherwise, in the absence of the cell, let's just consider this sort of a uniform bath with concentration that we can call C naught. And cells have particular proteins on their surface called receptors. There's receptors of many kinds, but usually receptors evolve to have high affinity for a particular type of molecule. And molecules will then encounter those receptors, and that will be sort of the first source of information that the cell has about this particular signal. Now, we'll make the cell a sphere. We're going to ignore the receptors, but they'll come back, okay? But just to get started thinking about this process, I'm going to sort of follow the thought process of Berg and Purcell. And one of the things that interested them greatly was the question of, if the real concentration outside of the cell is C naught, then how accurate, with what accuracy does the cell know that? So let's say the cell is just sort of measuring these molecules one at a time. What kind of precision or what kind of noise does that set on the cell's estimate of this background concentration C naught? So the idea, the way that I'm going to think about this, is that the cell, it doesn't know the real answer, C naught, but it's going to have some mechanism that is unspecified for the moment of estimating the concentration, and we're going to call its estimate C hat. Okay, so this is the real thing. This is the cell's estimate. And because it's obtaining this estimate by counting individual molecules, obviously if it counts one molecule, it doesn't really know much about the total concentration. Maybe if it counts another one and a certain amount of time has passed, it can begin to sort of do statistics, et cetera. But depending on how long that process happens and how it works, this estimate may be good or bad. In other words, there will be noise in this estimate. So the thing that interested Berg and Purcell is, what is the noise, which we can measure using the standard deviation in this estimate C hat. And in particular, they were interested in the ratio of that standard deviation, for example, to the mean of the estimate, which is something that we can call the fractional error, for example, the percent error. And so they calculated this through a couple of different means. Yes?
So you said that they can measure the single molecules, but that shouldn't be the generic picture, right? Are we talking about
Yes, so I should be clear. This is a different task than the sort of, if I detect a molecule, I'm going to do something task. This is more like, I want to know what the concentration is so that maybe if it's above some threshold, then I need to move. Or if it's below some threshold, I need to move and try to find more of it or something like that. Yeah. So this is more of a statistics gathering rather than a kind of like all or nothing response. Yeah. Does that make sense? Was there another hand, maybe? No. Okay. Good. So I was encouraged to try to wake you guys up a little bit. So maybe I'll try that and just ask, before we actually calculate anything, let's do some dimensional analysis. Physicists love dimensional analysis. They sort of it sets the stage. And let me just ask you sort of what are some parameters that this fractional error may depend on? Some properties of the concentration or properties of the cell so that we can, get a scope.
Size of the cell.
Size of the cell, absolutely. So I haven't given the cell a size yet. Let me give it a length scale, something like a characteristic radius. I'll call it A. If the cell is bigger, would you expect better or worse statistics? Better, right. So this is a noise quantity. So I'm going to assume that it will scale inversely with the size of the cell somehow, right? Dimensional analysis means I don't quite know yet how until I compare with other things that it might depend on. So what else? Diffusion. Diffusion sort of sets the rate at which molecules might arrive at the cell. Does diffusion go, so I can, of course, quantify that with the diffusion coefficient. Does diffusion go on the top or bottom? Top. You say bottom. You say bottom. Well, y can be positive or negative. Let's go with that. Okay. What else? The actual concentration, right. If there's just a very, very tiny concentration, the cell might never ever see a molecule. So this would be a very bad estimate. I've called the concentration C naught. What do you think? I guess I've just sort of explained where I think it goes. Top or bottom? Sorry? Bottom, yeah. I think I would agree. Right? If the concentration is very, very small, the error should be large, was my argument. Are we done? Sorry? Number of receptors? Yeah, number of receptors. I sort of hinted at the fact that I'm going to ignore the receptors at first, but they will come back, and we would expect that if the number of receptors is large, then the error should be low. I'm kind of going to assume, as they did at first, that there's infinity receptors, right? So any molecule that actually gets close enough is snatched up by the cell. Yeah? Observation time scale, absolutely. So, all of these processes that we've been talking about, or I've been sort of communicating, are sort of dynamic. I'm saying, oh, the faster things get there and everything. So we need some sort of observation time scale. And the longer the cell waits, I would argue, the better the statistics, so the lower the error. So I'll put the observation time scale down here and call it T. So T to some W. Okay, what else? Okay, maybe we can go with this, right? Let's remind ourselves what the dimensions of things are. Dimension of A is length, meters. Diffusion? Dimensions of diffusion? Anybody? Yeah, length squared per second. Observation time, seconds, and concentration is number of stuff per volume, so that's 1 over meters cubed. Okay. This may sort of already resolve the question about diffusion, I would think, right? Why am I saying that? So we see that the only times appear in diffusion and the observation time, and D and T need to multiply each other because this is a dimensionless quantity, right? So unless I'm forgetting something about time, which I very well may, d has to go on the bottom if t is on the bottom. Let's put it that way. So we can simplify this to something like a to the x, c naught to the z, and d and t have to be the same. So I'll sort of repurpose y and put it like this. Right? And that takes care of time. Everything else is length, so there's not much more we can say except for the fact that all of the multiples of length need to sort of cancel each other out, because once again, this is a dimensionless quantity. So I need to have something like x, which is 1 power of length, plus z, or actually minus 3z, because c naught is 1 over 3 powers of length. And then the product dt gives me 2 powers of length, so I have plus 2y. They all have to cancel, so that has to be 0. Right, so I can use that to solve for any one of these things, for example. So I get 1 over, I'll solve for x, 1 over 3z plus 2y is the power of a, and then c naught to the z dt to the y. Okay. Minus 2, thank you. Very good. Okay, so this says that the cell should be able to reduce error if it's bigger, if there's more stuff to measure, or if the stuff is arriving faster or the cell is waiting longer. I think that all is very reasonable. So let's see if we can figure out what z and y are with an actual model, right? So I'm going to start with the first model considered by Berg and Purcell. By the way, a lot of this comes from their paper in 1977, but then Howard Berg went on to write this nice book that, if you don't know, it's called Random Walks in Biology. And I'm shamelessly cribbing a lot of my stuff from here because it's just good. Okay, so the first model they considered is something which they termed a perfect sink, right? So this is what I mean by, I'm going to start by assuming that the cell has infinite receptors. And it just means that any molecule that arrives at the cell surface is immediately absorbed by the cell. Now, by the way, this is not always what receptors do. They don't always take molecules out of the system. Sometimes they just bind to them, and eventually the molecule unbinds, and the receptor is free to bind another molecule. So we'll consider that in the next sort of model. And it'll be interesting to compare those two types of reception. So, okay, so the perfect sink absorbs everything. And I'm going to call the number of molecules absorbed by this cell in a time t, the observation time t, I'm going to call that nt. So this is number of molecules absorbed. Now, we already know something about the statistics of this number because of how the molecules are getting there. So they're getting there by diffusion, and diffusion has very particular statistics. So if I were to ask you what we already know about the statistics of NT, what might you say? I don't know if you guys are familiar with diffusion statistics from other works or other lectures or other things you've done. So diffusion is sort of the ultimate randomizer of things in space, right? Which means that it has a couple properties. I have actually like air molecules diffusing in this room, right? If I were to draw an imaginary volume and ask, just take a snapshot and ask, well, how many air molecules are in that volume? And the answer would be the concentration of air times the volume of the sphere that I drew, for example. Except that's not always going to be right, because there could be pockets in the room with less molecules randomly and pockets with more molecules. So it's not just enough to tell me the mean number of molecules in that imaginary volume. I also want to know about the noise, the variance, or the standard deviation. And in a random process like diffusion, that number has a very particular property for the variance. It's a Poisson variable, which means that the variance is equal to the mean. So that's sort of a powerful starting point. I don't know necessarily yet what the mean number of molecules is, but I know that whatever it is, the variance or the standard deviation is going to be the square root of that mean, because this is a Poisson variable. I feel like this should work like a pen, right? Yeah. No. So what that allows me to do is, if I want to get the statistics of this estimate, then the cell is estimating it by this number, the number of molecules that it absorbs. So let me just make that explicit, right? So I'm assuming here that however it's estimating the concentration, whether it's doing some sort of internal computation, the only information that it has is this number of molecules it absorbs in a time t. And I think it's fair to assume that the estimate of the concentration should be proportional in some way to the number of molecules it absorbs. In other words, if it absorbed double the amount that it did yesterday, then it's safe to assume that the concentration is doubled from yesterday. So its estimator is going to be somehow proportional to this thing that it has access to. And so the fractional error in its estimate is going to be equal to the fractional error in this random quantity. And my point here is that because we know that things are just arriving according to diffusion, then this variable nt is a Poisson variable, which means all we need to know is its mean, and we already have its statistics. Okay? So the question boils down to, what is the mean number of molecules that arrive and get absorbed in a time t for a sphere? Right? How do we solve that? I mean, I know the answer, but just ideas? Or predictions for how I'm going to solve it? Yes?
Diffusion flux?
Sorry?
Diffusion flux?
Diffusion flux, absolutely. Absolutely. So the diffusion equation will give us this answer, right? The diffusion equation is going to tell us, on average, how many molecules flow into this absorbing sphere. The diffusion equation reads, yeah?
Just simply say that in steady state, the number, it's a steady state, so there's some flux per unit time, right? Some number of molecules per unit time.
Yes.
The total number of molecules should be proportional to the time. And then we'll look at that equation over there.
Yeah. Ilya wants to get z and y using the flux argument already, right? Is it?
Yeah, you're basically saying that t has to be there to the first power.
Yeah, that's a very good point. I think that's right. Now that we've we've understood that this error should go like root of that number, and that number should scale linearly with t. So we already know that y should be a half. That's your point, right?
Yes.
Yeah, very good. So Ilya's prediction is that y equals 1/2.
Can we do that? Is it legal?
Is it legal?
Yeah.
Well, I mean, everything is legal as a, that's how you solve every problem. You guess, and then you make sure that it's right. Am I answering that question? Okay. Can we do that otherwise? I think we can do that otherwise too, right, for z. I would expect that this number would increase with the volume of the cell, right? So that would suggest that no, I think I'm getting myself into trouble. So let's actually just calculate it and see why What would you guess for Z? Let me turn it back to you, actually. Yeah, this is actually, I would have guessed wrong, I think, doing it this way. You and I know the answer. Actually, maybe a few others. But okay. Let's solve the diffusion equation, as suggested, as correctly predicted. The diffusion equation reads like this. And let's start by explaining some symmetry, right? So this gradient could be expanded in spherical coordinates, but of course we know that the cell is spherically symmetric. This is a uniform concentration. So there should be no theta and phi dependence. And therefore, I'm just going to take the radial component of the Laplacian operator. And so this looks like d times, I can never remember, I think it's 1 over r squared, dr of r squared dr of c, right? And as Ilya pointed out, what we really just care about here is steady state. We imagine that the cell is sort of continuously sucking in molecules and they're being replenished from infinitely far away by the infinite bath, and that process is ongoing. And so what we really care about is in steady state, what's the continual flux into the cell? So in steady state, I get to set the time derivative to 0. And this problem becomes very easy, right? So, this we can ignore. The derivative of something is 0, so it's got to be a constant. So I'm going to say dc dr is some constant over r squared. And therefore, c as a function of r is the integral of that, which introduces some new constant, and we get b minus a over r. Okay, what sets a and b? Boundary conditions. What are my boundary conditions? There's one at infinity. What needs to be true at infinity? C is C naught at infinity. And? It's got to be 0 at A, right? Every molecule that actually gets to A, it snaps up immediately. So C of A is 0. And the only thing that can make these things true is for C of R to be C naught times 1 minus A over R, I believe, right? So if R goes to infinity, we're good. If R goes to A, we are good, right? Okay. So basically, as a function of R, this concentration is asymptoting to C naught and hitting 0 at A. Now, you mentioned the flux. So I have the steady state solution. How do I get the flux from that? Do you remember? You've volunteered for more than you thought.
Yeah, you can just, there's the flux equation which comes from the gradient, so you can just take that.
Absolutely. The flux is the gradient, exactly. So the steeper this slope is, the more things are going in. And in particular, the flux, which I can call J, anywhere at any radius, is d times the gradient, the dc dr, right? And it's usually given a negative sign, but because here we're interested in sort of the inward flux going backwards in the r direction, then I'm going to negate that negative sign. And I'm interested in particular in the flux at A, so I'm going to evaluate this at A. So I can take that derivative and I get A over r squared times C naught evaluated at A is just C naught over A. So this is D C naught over A. So that is the flux, meaning the number of molecules per area per time, right? That's how I'm defining flux here. And so what we really want is the total number of molecules over the whole area in the total observation time. So that is what I've called NT, or in particular the mean of NT. And so that's just the total surface area of the cell, 4 pi a squared, times the total time, times this flux, dc naught over a, right? And we get NT, which goes in the denominator and gets a square root, and gives us, oh yeah, a fractional error of 1 over root 4 pi a c naught dt. Okay, so we got the dimensional analysis results. We also got the actual prefactor. Is y 1/2? Yes, y is 1/2. And what is z? Z is also 1/2, right? So, so this works, right? This is consistent with our dimensional analysis. Y and z were both 1/2. I said something, though, earlier, which is that I would have expected that this number of molecules absorbed in a time t should go with the volume of the cell. And therefore, I might have expected an a cubed here. Why is that not happening? I don't think I actually know the answer to this, unless we think about it hard. Or somebody else thinks about it for me.
Definitely not the volume. It should be, if anything, it should be a squared, right? It's a surface that collects.
Okay, sure. Yeah, the surface is sort of the membrane in which things are flowing through.
But in reality, I mean, what happens is the molecules come in. They, even in a small object, the molecules will come in and hit it many times, right?
Yeah, but that
diffusion runs around, right?
Yeah, but
The
that's not happening here, though.
No.
I mean, technically.
The probability of hitting a square versus probability of hitting a line is the same.
I see. So you're saying even if this thing were shaped like a square, thus removing one of its dimensions.
Like a line, simply.
Well, like a line, you want to remove all 2 of its dimensions.
No, fine, square.
Yeah, I don't know. I think that's one way to think about it.
Could also be that because that also is proportional to the amount of things you're removing, so you're essentially depleting nearby. The larger area, also the larger the area of depletion, you're also
Okay.
and
So there's a competition there. Yeah, that's probably true. That's probably true. Okay. We might be able to actually make some intuitive progress on this question.
The actual argument
Yeah.
there is in fact the following, right? So you have a three-dimensional space, right? If you are falling onto a three-dimensional object in straight lines, dimensionality of your trajectory is 1, right?
Yeah.
So the total number of these trajectories that you are going to pick, you're going to actually absorb on this surface is going to be proportional to the area, to the length squared, right? And this square is a codimension to 1 to form 3, right? So you have a line going in one-dimensional object, and they're being collected by three-dimensional object. So it's the 2 dimensions that are left to collect the line, right?
Okay, I think I understand the first part of that argument. So you're saying if things were like shooting ballistically radially into the sphere, it would go as a squared.
As a squared, right? But now it turns out that diffusion trajectories are not one-dimensional. Right? If you actually
Right.
measure the dimensionality of diffusion, it's 2 minus epsilon, it's 2 basically, right? And so the codimension is 1, right? So if you have the diffusing particle is effectively not following a line, but it sweeps a 2-dimensional object. And so the codimension is 1, right? It's the 1 remaining out of 3 that is going to be picking up.
So because it's diffusive and not ballistic, it's equivalent to reducing the target by 1 dimension.
By 1 dimension.
Is that right? Okay.
So it's the same as trying to collect not straight lines by a ball, but trying to collect something that has a 2-dimensional shape, so membranes falling into a ball, and then it's only one dimension of the ball that matters, right? If it's membranes that fall into it rather than lines, right? That's
Okay.
cool.
Okay. All right. I buy that. I buy that. Okay. I want to go on to the next model, that sort of simplistic model that Berg and Purcell considered. And maybe there will be, because they did a lot of intuitive arguing for this next model, and maybe that'll be related to what we're talking about here. Okay, so the rationale is that, as I said, not all receptors work like this. They don't sort of always remove molecules from the environment. Sometimes they just hold on to them for a little bit and then release them back into the environment. And so to idealize that process, Berg and Purcell considered what they called the perfect instrument, or this has been later called something like a perfect monitor of molecules. So the perfect instrument is again a sphere. We can give it a radius A. But this time it's actually just permeable to the molecule, so it doesn't actually perturb the background signal. Molecules just diffuse in and out without really knowing that the cell is there in this idealization. Nonetheless, the cell reserves the right to have some sort of magical device to, at any given time, count the number of these molecules that is inside of its volume. Okay, so instead of sort of taking them out of the environment, it's just counting them. So I'm going to call n at any given time t is the number of molecules inside the volume of the cell. Okay. And the idea is that the cell can, still kind of average over a long time what this molecule count is and improve its statistics that way. And we're going to go through that calculation because so did Berg and Purcell. But the first thing that they did is they just sort of thought about it intuitively. And their argument was the following. So once again, this number inside of this volume, this is just like sort of the air example I was talking about. It has a mean, right? So this was the intuitive argument. So the mean of this number scales like the volume of the cell, A cubed, times the background concentration, C naught. And it also has a variance. It's a Poisson variable. So the variance in this number scales like the mean, also A cubed C naught. But then if the cell waits long enough, then the molecules that are currently inside this volume will diffuse out, and they'll be necessarily replaced by new molecules, right? And so if that happens a certain number of times within the window of the cell's observation time, then the variance should be reduced by that number. Okay, so if I make 2 measurements instead of 1, then the variance in their average is going to be the variance of any one of them divided by 2. So long as those measurements are independent from each other, right? Otherwise, I'm not really getting new information. So the question that I might pose to you guys is, how long does the cell have to wait before the batch of molecules gets refreshed? A squared over d, right? A squared over d is a characteristic diffusion time. It's certainly the only way to get something with dimensions of time with these variables, right? And it's sort of the characteristic time it takes a molecule to actually move through diffusion over a distance a. And since a is the only sort of characteristic length scale we care about here, or we even have, then the typical time for refreshing is a squared over d. So that means that the number of independent measurements that the cell can make in a time window capital T should be T over A squared over D, which is dt over A squared. And the variance should be reduced by this number. So that means the variance should go more like A cubed C naught divided by dt over A squared, which is A to the 5th C naught over dt. So then, using the scaling argument, we can ask, well, if the, can you guys see this down here? Question?
I have a quick question.
Yes.
What is the intuition for wanting independent measurements? Why don't you use correlated measurements and get some information out of the positions or numbers or so forth?
Yeah, so you can, in principle. I mean, like, it's not like the cell stops measuring things and then waits and then makes another one. And both the technique that Berg and Purcell used to actually calculate the answer and the technique that I will use to calculate the same answer are a continuous averaging process. So it's doing exactly that. But, you know, for the purposes of a scaling argument, you kind of just want to know the basic dimensions of how things scale. So I think this suffices for that. In other words, if you measured your next batch after a time that was much smaller than this, you would gain almost no information, right? So in that limit, that's what I'm trying to motivate here. Or, maybe we'll derive something just now and it won't be right, in which case we have to revisit your question, right? Okay, so if this is the variance and this is the mean, and the ratio sort of sets the estimation error that we've been talking about, then the ratio of the standard deviation over the mean here is the square root of A to the 5th C naught over dt divided by, inside the square root, the square of this, which is A to the 6th C naught. Things cancel. No, C naught squared. Things cancel. And we get 1 over the square root of A C naught dt. So lo and behold, this is, of course, the same scaling as in the perfect sink, right? So this is saying, at least if this intuitive argument is correct, that this method of measuring, in other words, just sort of monitoring what comes in and out, and this method of measuring, namely taking away everything that comes in, actually should give the cell equivalent information, or at least the error should scale the same way in both cases. Now, one method might be better than the other, right? Because we've sort of calculated this one exactly for the perfect sink. We don't know what the, we've done some scaling arguments here, so we don't know what the prefactor is here. So we're going to actually calculate this a little bit more precisely. But does anyone, before we do that, does anyone have a guess on which method will give better statistics? Absorbing all the molecules or just watching them? Absorbing? Watching? Those are the only options, actually. So,
Both the same.
or that's right, they could be equal. Thank you, Ilya. Why did you say absorbing?
If they are diffusing, then it's possible that you will be measuring the same molecule again.
That's a good point. In this case, this molecule might come in, it might go out, it might come right back in again, and the cell would think it's a new molecule. That's true. But how about an argument for absorption? I should have asked you first, and then he would have said the same thing. I would say this one might be better because it doesn't perturb the background signal. This one is, essentially creating a sink, right?
But cells are not
Yeah, actually, yeah, that's true. They're not fully covered by receptors, and even if they were, they'd probably be receptors of 100 different types or something like this. So we'll come to that, actually. That believe it or not, that was also a question asked in this paper by Berg and Purcell, whether that matters, essentially. But your comment, so how does that relate to your thinking about this question, about which is? Yeah, neither. Yeah. Okay, we could ask this question, but it doesn't matter because this is neither of them is how a cell actually works. Yeah. There was another comment, maybe. Yes.
I think observing them would be better because the error scales with 1 over the concentration, and the concentration at the cell surface is smaller when we absorb them.
The error scale is like 1 over the concentration, and when you absorb them, the concentration is actually smaller at the cell surface. So the error gets bigger. I see. So your argument is that your argument is that the scaling that we're seeing repeating over and over goes down with concentration. Concentration, the absorber reduces its own nearby concentration, and therefore it should enhance its own error by that logic, right?
I mean, on the other hand, the formula explicitly takes the concentration at infinity.
Yeah, exactly. Yeah, I would caution that this is C naught, right? Yeah, but yeah, that the intuitive reasoning might hold. I don't know. So then you would argue that the
prefactor should be smaller.
this would be a better measuring. This would be better statistics.
So
Okay.
the scaling should be the same, but the prefactor might be smaller.
Okay. All right. So maybe we can agree that at least among this audience, it's not immediately obvious. Okay. All right. So let's calculate it. And I'm going to do it in a certain way that was not done by Berg and Purcell. I don't know, maybe for some variety. You can go read how they did it using the autocorrelation function. I'm going to do it using something called Langevin dynamics. I just want to get a sense. Does that name mean something to people? Langevin equation and stuff? Okay, good. The reason I want to do it that way is because it will be useful when I want to generalize to more than one cell and models for how cells can collaborate to sense their environment. Okay, so the idea behind Langevin dynamics is that we can't use like the same flux argument as before because there's no flux, right? The cell is actually not perturbing anything. There's no boundaries of any sort. So instead, if we want to know about just the sheer statistics of the diffusive process itself, we have to do better than the diffusion equation, because the diffusion equation just gives sort of like a mean field answer. So we need to add noise to the diffusion equation, is my argument. And people do this in various ways, and don't get freaked out by the way I'm going to do it, but I'm literally going to add a Langevin term to the diffusion equation. The reason that freaks people out is because diffusion is already a noisy process. But I'm arguing that the solution to the diffusion equation is a nice smooth field. And by writing something like this, C dot equals D del squared C plus some noise term, that noise term is supposed to represent the particulate fluctuations on top of that smooth field. And if we prescribe the statistics correctly, then that's exactly what it will do. Okay. So yeah, Greg. See, I told you people would get freaked out.
It does. Can you derive this in a principled way?
I can derive the statistics of eta in a principled way. Yeah, and I'll. Do I need to?
I mean, so diffusion is sort of this smooth limit of a random walk. And so if you
Yeah, that's right. Diffusion is the smooth limit of a random walk, and eta is designed to retain the non-smoothness of the random walk. Yes, I can jump to the answer to your question because, yeah, this does freak people out if eta is just left sitting there. So, yeah, and I think we have all we need already. So, in order to get you more familiar with what object eta is, I can tell you what its cross-correlation is, right? That sort of gives everything you need to know about its statistics. So, eta, just like C, is a function of space and time, okay? The idea is that it endows C with some sort of fluctuation, so you should be thinking about C as a function of, x. a cartoon type of plot, not as just some background concentration C naught, but it has some diffusive fluctuations on top of it, which we can call delta C, right? So C is a function of space and time. Even if it's uniform, it's fluctuating, and so it's temporal, and it can be thought of as some background constant plus delta C, which is a function of space and time, right? And it's this eta, which is a function of space and time, that gives rise to this delta C. Now, I need to tell you, therefore, what is the cross correlation between eta at some position and time and eta at some other position and other time, right? This gives sort of all you need to know, or all you would want to know about the statistics of this process. And the answer is that there should be some strength, right? There should be some strength of the noise, which should depend on diffusion, I would argue. And it should depend on the mean concentration itself. And then there are usually in these sort of like Langevin Gaussian white noise processes correlators over time and space. And diffusion is delta correlated in time. This is sort of the random walk feature, idealized to sort of infinitely small time steps, where the direction you're going at one time does not correlate with where you're going to go in the next time step. But diffusion is not delta correlated in space, right? Because if you sort of think of this as a lattice and you have some certain number of molecules here, when one molecule moves out of that box, it moves into the next box, right? So there's got to be some correlation between x and x prime due to the essentially anti-correlations between neighboring boxes. Now, I'm just going to motivate what that is here, but you can derive it by literally starting with the lattice and writing down a lattice model and taking the lattice spacing to 0. And what you get is you get still a delta function in x minus x prime like this, except the anti-correlations induce gradient operators acting on this delta function. So you get a gradient in x dotted with a gradient in x prime. Okay? And this still probably freaks you out. I mean, this is not very common to have a derivative acting on delta functions, but everything can be sort of made fine in the limit of things. And more importantly, the way that people almost always deal with Langevin dynamics to calculate anything is to go into Fourier space. And the gradient operators will turn nicely into k's in Fourier space. And that usually freaks people out less, right? So
What does that mean of the noise?
what is the sorry? The mean, oh, the F, this thing, the strength of the noise. Is that what you're asking?
The mean of eta, I think.
Oh, the mean is 0. Yeah, sorry. That I skipped, unfortunately, foolishly. So the mean of this is 0. Yeah, we just want to introduce it as something that doesn't modify the mean field diffusion equation, but simply gives noise on top of it equally positive and negative. Thank you.
And the argument that it's Gaussian is, so you only need a second moment.
Well, the pragmatic answer is that I only, the premise only cares about the second moment. I have a hunch that it actually is Gaussian, so to speak. Like diffusion doesn't have third moments or something. I have a hunch that can be stated in some exact way, but that's only a hunch. Yeah. I don't know. Do you have insight on that or no? Okay. Right, and of course this is really only the only parameters in the problem, so it has to be like this, and we can deduce what this needs to scale like, right? Because eta has the dimensions of concentration per time, right? So it is 1 1 over time meters cubed. And so eta eta is 2 factors of time and meters to the 6th on the bottom. But this already has a 1 over time, right? And so we just need 1 time on the bottom, and that's going to be given by the diffusion constant itself. Now we have a meter squared up top. We need it to become a meters to the 6th on the bottom. This has 3 meters on the bottom. These each give 2 more. So that's 5th on the bottom. So I need 1 factor of C naught to give me 8 on the bottom to cancel with the D and give me the 6th, right? So this is just DC naught. And in fact, if you derive it, like I say, from the lattice, you get a 2 here. Yes?
I have a question about this correlation with space-time.
Yes.
So it's not clear to me why this does not depend on the difference in the time. Because somehow I would have expected that the correlation in the space should
Yes. Yeah. Yeah, that's a great question. That is a great question. I would like to answer it by saying that space and time are intermingled until you take the lattice spacing to 0, in which case you can sort of separate it as, you know, the extreme thing being delta correlated in time and the extreme thing being just a derivative in space instead of some sort of delta x spacing. I don't actually think that's the answer, though, because the way you would derive this on a lattice is you would simply say that, you know, the only reactions that can happen are transitions from one box to another, and those transitions are also delta correlated in time, right? That's how you typically do a Langevin dynamics without space in the picture. So I have sort of assumed an order of events here. I've assumed that things are delta correlated in time within a lattice box, and then I take the spacing to 0. Yeah, I don't know if that's a problem, but that's essentially how you get this. Right, so the Fourier analog of this, which maybe is a little less freaky, is that the Fourier transform, which is now a function of k vector and omega, you know, sort of eta star eta. This is how you would write the cross correlator in Fourier space with a k prime and omega prime, is simply the strength again times, so that the delta correlator in time becomes a delta correlator in frequency, and I need my 2 pi for the Fourier transform, and then we get a 2 pi cubed. These gradients become a k squared. I mean, it becomes a k and a k prime, but really because of the delta, we get just a k squared, and we get delta of k minus k prime. So that's purely algebraic, and it's more, as we'll see, it's more useful. And I hope it does make sense that the sort of strength of this noise scales with both the diffusion and the concentration, right? The more molecules there are, then proportionally the more fluctuations there are. And same with the diffusion. Okay, so that was a lot of don't worry kind of discussion to motivate the addition of this term. Okay, but this is exactly the term with which we're going to calculate the actual fluctuations in the time average of this variable, right? Because I've sort of only introduced the time averaging process loosely here. I mean, what we really want is, if we are solving this equation with the correct statistics, then those statistics should propagate to the variables we're interested in, which are n, the number of molecules at any given time inside of this permeable cell, which would be the integral over the volume of this fluctuating concentration quantity. And then the thing which I'll call nt again, which is, in this case, the time average of this quantity, right? In the absorbing case, it was the accumulated number. In this case, I'm just defining it as the time average. So it's the time average 0 to t of n of t, right? So the idea is to go from this eta to give me the correlations in the concentration, which will give me the correlations in this number, which will give me the statistics, the variance, let's say, of this time average. Right? And that's what I'm really after to do this calculation. Okay, is that a clear plan? Because then all we need to do is execute the plan. Okay. So the way we're going to do this is to use what's called the power spectrum. Is that a familiar phrase to people? Have you heard it before at least? Yeah. The power spectrum. So the power spectrum is a function of frequency, and we're going to do it for this variable n. And it's defined as the integral over one of the frequencies in the cross correlator over the cross correlator. So, and it's the cross correlator of the fluctuations in this case. And it's in Fourier space. So this is the Fourier transform of the fluctuations in n evaluated at omega prime, complex conjugate, times Fourier transform at omega. Okay, and the reason why we're going to do this is because if you want the variance in the time average of a quantity, that is simply the low frequency limit of its power spectrum. So I don't know if you guys are familiar with that result. Yeah, so I'll write it down and then I'll repeat it. Right? So the result is that if you want the noise, or the variance specifically, in the time average of a quantity, then that is equal to the low frequency limit of its power spectrum over the averaging time. And that's only true, by the way, if the averaging time is much longer than the longest time scale governing the process. Okay, and that assumption is made use of in a more crystallized way in the derivation of this result. And that derivation relies on the fact, essentially, that the autocorrelation function, which is sort of more directly related to the actual variance, and the power spectrum are Fourier conjugates of each other. But it's basically just a lot of math, right? So I was also told, luckily, at the very beginning that, like, you guys are strong, and if it's just about evaluating integrals, we can maybe do that offline. So if you're willing, you can believe me on this, and if you're curious, we can talk about it offline, if that sounds good. But that's the idea. So this is what we want. This is how we're going to get it. Use the power spectrum. And so now it's just about plugging in the pieces, essentially. So, okay. So first of all, it should be hopefully clear that the mean of this variable, because it is the time average, is simply the mean of any instantaneous count, which is just the volume 4/3 pi a cubed times the background concentration C naught. Okay, that's the mean. For the variance, we're going to need this power spectrum. And so to do that, we need to know what these fluctuations in n are, and they're related to the fluctuations in C, which are related to eta. Right? So the fluctuations in n in real space are just, well, no, in Fourier space is what we want. They are the Fourier transform of the fluctuations in n in real space times e to the I omega t, and delta n is related to delta c the same way n is related to c, right? So delta n is just the integral over the volume of delta c of x and t. Okay. So I don't want to belabor this. I think that's probably the best strategy here. But I want to make all the pieces clear, right? So the point is that we want the power spectrum, so that requires delta n Fourier transform. Here's delta n. We get delta n from delta c. There's one more piece, right? So how do we get the delta c in Fourier space? Well, we simply Fourier transform the diffusion equation with this added Langevin term, and then we can use the Fourier part of this cross-correlator, right? And that last piece is pretty easy, right? So that last piece is just Fourier transforming this boxed equation up here. And, well, actually first plugging in the fact that c is c naught plus delta c. So the derivatives actually don't act on the c naught, they just act on the delta c. So it's actually the same equation for delta c. Just want to make sure that's clear. Now we can Fourier transform this, and that turns the time derivative into a minus I omega, turns the Laplace operator into a minus k squared, Fourier transforms the eta, and now this is algebraic, and we can solve for delta c. So delta c as a function of k and omega is nothing more than eta tilde over dk squared minus I omega. Right? So this is related to delta n is related to delta c, which is of course related to its own Fourier transform delta c, which is given by this. You plug all that into the cross-correlator, you end up with a cross-correlator over eta, and that's here. And as you can imagine, these delta functions come in very handy, and they collapse a lot of the integrals that you've accumulated. Okay? And so I'm just going to then write down the result. So what you get as a result is the following. And I'm already going to take the frequency to 0. And what you get is you get the 2 c naught over d, right? The c naught comes directly from here, the d here, and the d here interact to bring d down to the bottom. And you get an integral over the volume in x space and x prime space, and an integral of a remaining k space of e to the minus I k dot x minus x prime over k squared. Okay? When everything cleans up and the integrals collapse, these are the only integrals that remain. Moreover, this is just some three-dimensional math, right? These are just things that you can break into spherical coordinates and actually just do these integrals. And the only parameter that's actually in here that doesn't make this sort of a dimensionless problem is the volume. You're doing this over a sphere of radius a. So in other words, the only answer that can come out of this once you do the math is something that depends on a. And the answer is, once again, if you're really curious, we can go through the derivation. The answer is 8 pi over 15 a to the 5th. And I think that needs to be the right factor of A, right? Because there's only one K and there's 6 lengths. So that's 5, length to the 5, right? So it has to be A to the 5th. And 8 pi over 15 is what we've been working so hard for here. Okay, so you plug all this. So you plug this into here. You get the ratio of this to the mean, and you find that the fractional error in this estimate, if it is indeed proportional to the fractional error in this quantity, is the square root of 3 over 5 pi times, as we've been promised, the A C naught dt. So this is the fractional error for this monitor, this perfect instrument. Now we started with the question of which we thought would be better, which we thought would be lower error, the absorber or the monitor. What's the answer? The absorber. Yeah, actually, because 3/5 is higher than 1/4. And root 3/5 is also higher than 1/4. Root 3/5 is about 1.5 or so higher than 1/4. So the absorber is better. And so you were right, actually. And what was your argument?
The molecules that go inside, go outside, can get inside.
Exactly. The absorber doesn't double count. And that's my intuition as well, and others, right, that I've seen written. So indeed, the instrument doesn't know whether a molecule that it's counting has been counted before. And if it is something that it's been counted before, then it's not independent. So not all of its measurements are independent, whereas the absorber never double counts. So I think that is what's playing out in, but it's not that big of a deal, right? It's like a factor of 1.5. Okay, yes, Ilya.
So we've got a factor of 1.5
Yeah.
or something like that, right?
Yeah.
How big of a factor is going to be if this object is not spherical?
Yeah.
I mean,
So that's
is it worth it fighting for these factors, given that we do
this
not really-
is a bit of an academic exercise just to build intuition. Like, you know, if you have like two strategies like this, which is better. And I would agree, 1.5 doesn't really
But I mean,
shouldn't really make a difference
it's
itself.
sort of we sort of should understand this in the sense that fine, even if you're double counting, you'll get a factor of 2, right? Even a triple counting, you're going to get a factor of 3, right? But it would be very hard to believe that you are infinitely counting, right? That the molecule will keep on coming back infinitely many times before it just disappears somewhere,
Yeah.
right? And so we'll not get different scales, right? We'll get a factor of a few from the very beginning,
Yeah.
right? So maybe we're missing bigger things in the problem. Right?
Yeah, and I think actually that goes back to the question that was asked earlier, which is why are any of these relevant? We know cells have receptors that cover nowhere near all of the surface. And so that's actually what I want to talk about now, and that will directly address your comment about, you know, okay, is it double counting, triple counting, infinitely counting, you know, that kind of question. Right, so this was sort of, I would say, one of the more realistic things that Berg and Purcell worried about, which is that what if your cell, you know, I mean, in reality your cell is neither of these things. In reality it has specific receptors on the surface. And so we can think about whether the results we've obtained about the statistics in these two cases are relevant by first just imagining the first case, the absorber, and asking, well, let's say that not all of the cell surface was absorbent. Let's just say little patches on the cell surface were absorbent, and there weren't that many of them. Well, how much does it actually absorb compared to what it would absorb, given that the whole surface is absorbent, right? So that's the question with individual receptors. So, or at least that's how they posed it. How much does the cell actually absorb. Okay, so the way they thought about this was from the perspective of a single molecule. Yes?
Before you do
Yeah.
the calculation, just curious from biology,
Yeah.
independent of the calculation, is there some intuition about whether this should be really a few receptors that should be covered in receptors?
Oh, you mean sort of what are the data?
Yeah.
Yeah. So typical receptor numbers on cells in our body, for example, are usually something like thousands or tens of thousands or more. But receptors are pretty small. They're several orders of magnitude smaller than the length scale of the cell. So that actually doesn't cover that much of the area of the cell surface. Berg and Purcell were thinking specifically about bacteria, and I think in their case, the receptors were receptors for attractants or nutrients for those cells, and those are well studied. And I think that bacteria have chemotaxis receptors on the order of maybe hundreds to thousands, or maybe also tens of thousands on their surface as well. So that's the orders of magnitude that we're talking about here. Yeah.
Maybe this is a stupid question. Was that known to Berg and Purcell? Like, did they have the data available in 77? Did they have a clear picture of?
Yeah, good question. Yeah, not a stupid question. It's a good question. It's about what was known in the field at a certain time of the field. I don't know.
They knew how many different types of receptors E. coli has.
Yeah.
So, well, that was Adler who, in late 60s, early 70s, basically measured how E. coli chemotaxis towards everything, right? Just everything in chemical libraries, right? And then, so they knew the number of
The number of types,
the
but
number of
yeah.
types, right? They also knew, roughly speaking, that the receptors are not uniformly distributed over the cell surface, and I forget how they knew this, but they did.
Yeah, so E. coli are not spheres, for sure, and they have poles, and I think you're saying there's more receptors on the poles than
And
the...
I think that from that point on, knowing the size of the receptor, they more or less knew what is the upper limit, how many receptors are there, and so E. coli poles are pretty much covered with receptors.
Okay. Yeah, that's a good way to estimate. Yeah. Okay. Yeah, question?
What about the fact that you have a receptor and it binds to something and it cannot bind with something?
Yeah, the receptor is now occupied, and it's sort of offline until it unbinds that one particular molecule. Yeah, actually, that, believe it or not, that was also in this paper. And so before considering a cell covered in a certain number of receptors, they thought, well, what about a single receptor? And let's ask the same questions that we did about the entire cell, but about a single receptor. What are the statistics of its measurements? And what happens is, instead of just, I'll call it the fractional error, instead of just going like 1 over root a c naught dt, the a gets replaced with the length scale of the receptor. I'll call it S, for example. So now we're sort of imagining one receptor as sort of an object that can, let's say, bind and unbind molecules repeatedly, and asking what are its statistics. So its length scale is S. But also, there's a factor which is 1 minus the fraction of time in which the receptor is bound. So if it's always bound, then p goes to 1, and the error is infinity because it can't measure anything. If it's never bound, then we get the same result. However, this is hiding the fact that then the mean is actually very small. Both the mean and noise are small. You know what I mean? So it's not really measuring anything if it can't ever bind anything. You see what I mean? So, if it's somewhere in between, then yes, this puts in another factor of order 1/2 on the bottom. Yeah?
Can you collapse the noise in the error of the measurement in the error of the fluctuations?
Can I collapse the noise in the error of the... I don't think I understand.
So the receptor is also going to be noisy, right?
Yeah.
So it's also going to have some false positives, it's going to have
Yes.
So there's going to be some noise.
Ah.
And can I just say, okay, you know what?
Yeah.
Have some noise
I see.
there, it's the same.
I see. Yes, absolutely. And this was very much on the mind of. The speaker on Friday, Bill Bialik, was on Friday, right? Okay. Yes. So in 2005 or so, he and a postdoc at the time, Seema Setayeshkar, asked this question, and they said, okay, how can we actually think about this result in the context that we also know that receptors themselves have noise, right? They're not perfect at gathering the data. And basically what happens there is, instead of just getting a scaling like this, you get another term that's due to the binding and unbinding randomness, the randomness in that process, the binding and unbinding of molecules to receptors. And I don't precisely know how that scales, but for example, you'll have like a binding rate on the bottom, for example, where if, it can't just be this, but somehow maybe like the ratio of binding rate to the diffusion limited association rate. So actually, I'm just guessing here, but maybe it's something like this, 4 pi AD or something. Okay, take this with a grain of salt. But the point is that there's another term that depends on the binding kinetics that can only increase the noise, but it's an additive term, right? So if receptors were perfect, you would reduce back to the noise that's already intrinsically there due to the diffusion of the molecules themselves. Okay. Right, we have a hard cutoff here, so I'm just going to set up the problem, and then, am I talking again on Wednesday or tomorrow? I guess it doesn't matter, but next time we'll continue. Sure.
Tomorrow.
Yeah, but I think, is David here?
Thursday.
Yeah, but I think, so David emailed me and we might swap. That's why I said, okay, anyway. Okay, so here's the idea, right? So we have a cell, and now we don't consider it anything perfect like this. Instead, we just have, it has like little patches, which are sort of the idealization of receptors. Little portions of its surface where if a molecule hits that portion, it gets absorbed. If it doesn't, then it doesn't, which means what happens? Well, it can probably bounce off, and then maybe it comes back and then bounce off. And this is sort of what Ilya was getting at with like double arrival, triple arrival, etc. So this is how Berg and Purcell thought about this process. And they thought about it from the perspective of a single molecule. And they asked the following question. What is the probability that this molecule will start near the cell and actually not be captured by the cell? What's the probability that it'll escape forever? Right? And so there's a couple ways that can happen, right? So it can start near the cell and just never get there, right? It can sort of, in 3 dimensions it is possible to diffuse away and never come back, right? So, we can call that probability P, for example. Or it could start near the cell, it could hit the cell, and it could get lucky, so to speak, and it didn't hit a receptor, right? So then it bounces off, and maybe then it is able to diffuse away forever, right? I'm giving the molecule free will here, like it wants to survive. But so then this happens with 1 minus p. It did not escape the first time. Then there's another probability that it did not hit a receptor. Call that q. And then it escapes, right? Yeah, okay, I got my notation backwards from my notes, so we're going to see how long I can go without screwing up. So, or this can happen over and over, right? So, or it misses the receptor, comes back, it actually hits again, it misses, it comes back, and then it goes away forever, right? So, 1 minus p, q, it comes back, so this is a 1 minus p, a q, and then it escapes forever, p. right? And the point is that this could keep going, right? So the total probability that it escapes is then P plus 1 minus P QP plus 1 minus P squared Q squared P plus da-da-da-da-da. Or I can pull out a P and make this a sum from 0 to infinity of 1 minus P times Q to the nth power. This is a geometric series. It's less than 1. And so we know the answer is just 1 over 1 minus that ratio. So this looks like P over 1 minus the quantity 1 minus P times Q. Right? And then, we don't actually really care about the probability that it escapes. This was just the easier way to calculate it. What we really care about is the probability that the molecule gets absorbed. But that's just 1 minus the probability that it escapes. And, that's what we want to compare with 1. Because if it's a perfectly absorbing sphere, then the probability is 1. So, actually, if it's a perfectly absorbing sphere, the probability is 1 minus P. But anyway, this gives the right idea. So then the remaining question is, what is P and what is Q? Right? So I have time for Q. P we'll do next time. So Q, I think, we can make a very reasonable approximation by just considering the molecule would be arriving sort of at random at anywhere on the surface, in which case the probability of not hitting a receptor would be the fraction of the area of the cell not covered by receptors, right? So that would say that Q is the fraction not covered by receptors, which is the total area, 4 pi a squared, minus the fraction covered by receptors. Now let's say there's, R total receptors. So that would be R times, and we can, assume that they're circles or something, right? So this would be R times pi s squared, if s is their length scale. That divided by the total surface area, right? Now, that's a reasonable approximation for Q, so long as it's fair to say that every arrival of a new molecule is sort of seeing the cell for the first time. Now, that would sort of require us to, in these cases where it goes away and comes back, that would require us to have some argument about how far it needs to go away before coming back. I don't think it would need to go, all the way away, sort of total length scale of the cell, but it does need to go far enough away to sort of, if it was near one receptor, to sort of guarantee that it's not still near that receptor to be an independent arrival event. So I would say the length scale of relevance here is S, the size of the receptor. So I would say as long as it goes at least S away from the surface of the cell, we can sort of be confident in considering this the failure probability of being absorbed. Okay, if that clock is like super accurate, then I'm going to stop here.
All right, thank you.
Yep.